In this part of the Neurocomputers and Deep Learning course related to associative memory, you will learn how to implement accretive heteroassociative memory using recurrent neural network called BAM, that is bidirectional associative memory. The bidirectional associative memory BAM introduced in COSCO 88 is a recurrent network designed to work as heteroassociative memory. In the bidirectional associative memory, we have two layers, which are X layer and B layer. The neurons in this layer are called X1, X2 up to Xn. We have M neurons, and in this layer we have N neurons. They are called V1, V2 up to Vn. BAM network consists of two sets of neurons whose outputs are represented by vectors X element of Rm, here we have M neurons, and V element of Rn, we have N neurons here respectively. Having activation defined by the pair of equation, the time derivative of the activation of neuron I in the X layer is equal to minus alpha I, the activation of the neuron I. For this one, we are trying to find out what is the time derivative. We are using the activation at that time, plus summation j from 1 to n. We are considering the neurons here. For each neuron in this layer, on the activation of neuron Vj, we are applying the output function and we are taking the summation Wji, the connection weight from the neuron J to I for each J is multiplied by the output of that neuron. The output function applied on the activation is corresponding to the output of the neuron, plus theta I for the neuron I. I is changing from 1 up to m. For a neuron in the layer B, the time derivative of the activation of neuron J is equal to minus beta multiplied by the activation of that neuron itself, plus we have a summation I from 1 to m. We are considering all neurons in the layer X, and on the activation of neuron Xi, we are applying the output function, so this is corresponding to the output of the neuron I in the X layer. For each neuron I here, we are considering the connection weight from that neuron to neuron J, and we are multiplying with the output value of the neuron Xi, and we are doing this for all neurons in this layer. I from 1 to m, we are multiplying the connection weight with the output of that neuron, plus we have here, instead of theta I, for each neuron we are considering the threshold value. J is changing from 1 up to n, where alpha I, beta j, theta I, and pi I are positive constants for I from 1 to m and j from 1 to n. Here f is the tangent hyperbolic function and w is the matrix, each entry is wij, is any n by m real matrix, and also the columns of the matrix W is corresponding to the connection weight matrix of the neurons in this layer. If we consider the W transpose, then each row is corresponding to connection vectors of the neurons in the B layer. The stability of the BAM network can be proved easily by applying Cohen-Grossberg theorem by defining a state vector Z element of Rn plus m such that Zi is equal to xi for I from 1 to m, and it is equal to Vj for j I minus m when I is larger than m. In that case, we are using Vj where j is equal to I minus m. I is between m and m plus n. That's that obtained through concatenation of x and v. So we are considering the neurons here, and then we are concatenating with the neurons in the V layer. Either we are using the activations or the outputs of these neurons. Since BAM is a special case of the network defined by Cohen-Grossberg theorem, it has a Lyapunov energy function as it is provided in the following. The energy in terms of the x vectors and v vectors here is equal to double summation. Here the connection weight between the neuron I and J, where I is in the X layer and J is in the V layer. I is from 1 to M, J is from 1 to N. We are considering the Wij multiplied by the output function applied on the activation of neuron Xi here, which is equal to output of neuron Xi, multiplied by the output of neuron Vj. So each neuron here and neuron there, we are multiplying their outputs, and also the connection weight, we are applying double summation, and then we have a minus here. Plus I from 1 to m for each neuron here, alpha I, multiplied by the integral of the derivative of the output function at point A, multiplied by A dA. This is the integral term in the energy function. Here we have an integral from 0 to current activation value of that neuron. And similarly for each neuron in the V layer, here we have the integral, the activation from 0 to AVI, so V is corresponding to activation here, the inverse of the output function multiplied by the activation there, and then we are taking the integral. And then we are calculating the integral. And these are the integral terms. And then we have single summation terms. For each neuron in the X layer, we are considering their output multiplied by the theta value for that neuron. Here we have summation, I from 1 up to m, and here we have a minus sign. And similarly for each neuron in the V layer, we are considering the output there, F applied on the activation, multiplied by the, again, phi j value, given that this is corresponding to threshold. The discrete BAM model is defined in a similar manner to discrete Hopfield network. The output functions are chosen to be Fa equal to sine A, and states are excited as xi k plus 1. The output value of the neuron xi at time k plus 1 is equal to f function applied on the activation of that neuron at time k is equal to 1 if the activation of that neuron at time k is greater than 0. It is minus 1 if the activation is less than 0, and it is remaining the same if the activation is 0. Where the activation of neuron xi is defined as j from 1 to n, we are considering each neuron in the V layer, and on their activation, output function f is applied, so this is corresponding to the output of the neuron Vj. For each neuron, we are multiplying the output of that neuron by the connection weight from that neuron to our neuron xi. And here j is from 1 to n, and here we have plus theta I. I is from 1 to m. So we are considering each neuron in the X layer. And similarly, for each neuron in the B layer, for neuron Vj, the output of that neuron at time k plus 1 is calculated by applying the f function at the current activation of that neuron. And this f function is defined such that if the activation of the neuron Vj at time k is greater than 0, output is set to 1. If it is less than 0, the output is set to -1, and it is remaining the same if the activation of that neuron is equal to 0. And very similarly, and similar to this one, the activation of the neuron Vj is calculated as the connection weights from the neurons in the X layer multiplied by the output of those neurons in the X layer. Here I is from 1 to m, so we are considering each neuron in the X layer plus the threshold. And here J is from 1 up to n. We are considering each neuron in the V layer. In compact matrix notation, it is shortly X vector, the outputs of the neurons here at time k plus 1 is calculated as f function applied on the weight matrix transpose multiplied by the V vector here at time k. And for the neurons here, the output vector V at time k plus 1 is calculated as f function applied on the W multiplied by the X vector here, which is just calculated at this step. This is at time k plus 1. And here notice that all the neurons in this layer can be updated at once synchronously by using the values in the V layer, and similarly all the neurons in the V layer can be calculated synchronously by using the neuron outputs in the X layer. In the discrete BAM, the energy function becomes the integral terms drop, and we have double summation for each neuron in the V layer and for each neuron in the X layer. We are multiplying their outputs with the connection weights between them, and we have a minus here, and we are considering each neuron in this layer. We are multiplying their output with the threshold values, and we are summing them from I from 1 to m, and also we have a summation for the neurons in the V layer, and here we are multiplying their outputs with the threshold values, and we are applying summation J from 1 to n. And notice that we have minus signs before the, here notice that we have minus sign before the summations. And this is satisfying the condition. The change in the energy is less than equal to 0 for each update in the network. This implies that the network is stable. So the energy is decreasing at each update of the neuron outputs, and this implies the stability of the system. The weights of BAM is determined by the equation weight transpose equal to Y U transpose. Remember that Y is the matrix in which each column is corresponding to the Y part of the memory patterns to be remembered, and U is the matrix for which each column is the U part of the exemplars to be remembered. And here we have transpose. This is weight transpose is equal to Y U transpose. For the special case of orthonormal input and output patterns, we have the F function, sign function, applied on weight transpose UR is equal to F applied on, instead of W transpose, we are writing YU transpose and multiplied by UR. UR is one of the columns here. Because the U patterns are orthonormal, for any column here in the U matrix, the transpose of that column multiplied by UR is the inner product of that vector with UR because the patterns are orthonormal. If that column is not R, it results in 0, otherwise it results in 1. Because of that, only for the column R here it is resulting in 1. So we are selecting the column R of the Y matrix. So it is equal to F applied on YR. This is resulting as YR, and because this is the sign function, none of the element here in the Y vector is 0. They are either -1 or +1. When we apply the sign function, we obtain YR as it is here. And similarly, for the other part, notice that here instead of W transpose, for the other side we have W here. WYR is transpose of this one, which is UY transpose, and multiplied by YR. So this multiplication is resulting in UR if the exemplars in Y are orthonormal. After that, if we apply the sign function on UR, we obtain UR itself. So this is indicating that exemplars are stable states of the network. If we start with UR by multiplying the weight matrix and applying the F function, we are converging to YR. At once, we are obtaining YR. And similarly, if we are applying UR at the V layer, at one step at the X layer, we are obtaining YR, which is resulting back UR in this layer. So this is a peak state of the network. So indicating that exemplars are stable states of the network. And similarly, if we apply any YR pattern here, then at once we will obtain UR in this layer. In return, we will obtain UR here. So this is the stable state of the network. Once we are from this layer calculating the outputs there, and from that one, we are calculating back what are the outputs in this layer. And after that, the outputs are not changed. Whenever the initial state is set to one of the exemplars, the system remains there. For arbitrary initial states, the network converges to one of the stored exemplars, depending on the Bayesian attraction in which X0 lies. For the input patterns that are not orthonormal, the network behaves as it is explained for the Hopfield network.